Structure of metamorphic rocks. Metamorphic rocks are formed when existing igneous, sedimentary, or even older metamorphic rocks undergo changes due to heat, pressure, and chemically active fluids. These processes alter the mineral composition, texture, and overall structure of the rocks without melting them. The structure of metamorphic rocks varies depending on the degree of metamorphism, the original rock type, protolith, and the dominant geological forces at play. 1. Foliated structures. Foliation is a key structural feature of many metamorphic rocks, resulting from the alignment of mineral grains under directed pressure. Foliated rocks display a layered or banded appearance and can be classified into different types based on the intensity of foliation. Slaty cleavage. This occurs in low-grade metamorphic rocks, such as slate, where fine-grained platy minerals, mainly clay and mica, align under pressure. The rock can split into thin sheets. Phylitic structure. Phyllite forms at a slightly higher metamorphic grade than slate. It has a silky or slightly wavy appearance due to the fine-grained mica minerals reflecting light. Schistosity. Schist is a medium to high-grade metamorphic rock with larger mica, chlorite, and amphibole minerals aligned in a distinct foliation. The rock has a visible, glittery texture. Gneissic banding. In high-grade metamorphic conditions, minerals like feldspar, quartz, and biotite separate into distinct light and dark bands, forming a gneissic structure. Gneiss is one of the most strongly foliated metamorphic rocks. 2. Non-foliated structures. Some metamorphic rocks do not develop foliation because they form under conditions where pressure is not directed or because their mineral composition lacks platy or elongated minerals. These structures include granoblastic texture. Found in rocks like marble and quartzite, this texture is characterized by equidimensional grains that form interlocking mosaics without any preferred orientation. Hornfelsic texture. Hornfels forms through contact metamorphism, where high temperatures recrystallize the rock without significant deformation. The texture is typically fine-grained and dense, with randomly arranged minerals. Porphyroblastic texture. Some metamorphic rocks contain large mineral crystals, porphyroblasts, embedded in a finer-grained matrix. These porphyroblasts, such as garnet or staurolite, grow during metamorphism. 3. Lineation structures. In some metamorphic rocks, mineral grains may align in a linear rather than planar fashion, leading to lineation. This structure is commonly seen in rocks affected by strong tectonic forces. Types include mineral lineation, alignment of elongated minerals like amphibole or sillimanite in a single direction. Stretching lineation, formed when mineral grains or rock fragments are elongated due to intense deformation. 4. Deformational structures. Metamorphic rocks often show evidence of intense deformation caused by tectonic forces. These structures include folds. Compressed layers of foliated metamorphic rocks may develop large-scale folds due to pressure. Boudinage. Competent layers of rock get stretched and broken into segments that resemble sausages. Shear zones. Rocks exposed to intense shearing stress may develop a myelinitic texture, where minerals are intensely deformed and elongated. Conclusion. The structure of metamorphic rocks provides important information about their formation history, the intensity of metamorphism, and the geological conditions they experienced. Foliated structures indicate strong directional pressure, while non-foliated rocks suggest either uniform pressure or mineralogical resistance to alignment. Studying these structures helps geologists understand Earth's tectonic history and the processes that shape the crust. Sonu Dedin. Primary structures of metamorphic rocks. Metamorphic rocks originate from pre-existing igneous, sedimentary, or older metamorphic rocks that have undergone transformation due to heat, pressure, and chemically active fluids. During this process, the original rock structures may be altered, destroyed, or preserved to some extent. The term primary structure in metamorphic rocks refers to the original features inherited from the protolith, parent rock, before metamorphism occurred. These structures provide crucial information about the rock's history, including its depositional or magmatic environment before metamorphic changes took place. Primary structures in metamorphic rocks can be categorized into different types based on their origin, including sedimentary, igneous, and deformation-related features. 1. Sedimentary primary structures in metamorphic rocks. Many metamorphic rocks retain sedimentary structures from their original deposition. These features indicate that the protolith was a sedimentary rock before undergoing metamorphism. A. Bedding, stratification. Original bedding layers from sedimentary rocks can sometimes be preserved in metamorphic rocks. In low-grade metamorphic rocks, such as slate and phyllite, bedding may still be visible, though often distorted. In high-grade metamorphism, bedding may become folded or obscured by foliation. B. Cross-bedding. Found in metamorphosed sandstone, metasandstone, or quartzite. Original cross-laminations, which form due to current or wave action in sedimentary environments, may still be visible. In some cases, cross-bedding becomes accentuated by differential weathering. See ripple marks. Ripple structures can sometimes be preserved in fine-grained metamorphic rocks like quartzite or marble. Their presence suggests that the original rock was deposited in shallow water environments, such as riverbeds or tidal zones. D. Graded bedding. Originally formed by turbidity currents in deep-sea environments. In metamorphic rocks, graded bedding may be deformed but still provides clues about the original depositional setting. E. Mud cracks and raindrop impressions. These features can occasionally be found in low-grade metamorphic rocks derived from mudstones. They indicate subaerial exposure of sediments before burial and metamorphism. 2. Igneous primary structures in metamorphic rocks. When igneous rocks undergo metamorphism, some of their primary magmatic features can be preserved. These include A. Flow banding. Found in metamorphosed volcanic rocks. Originally formed by the movement of lava during cooling. Often preserved in schist and gneiss derived from volcanic rocks. B. Vesicles and amygdaloidal structures. Vesicles, gas bubbles trapped in lava, may be preserved in low-grade metamorphic volcanic rocks. If filled with secondary minerals such as quartz or calcite, they become amygdaloidal structures. C. Pillow structures. Formed when basaltic lava erupted underwater, creating pillow-shaped structures. Pillow basalts can be metamorphosed into greenstone, retaining their pillow morphology. D. Igneous layering, cumulate structures. Found in metamorphosed mafic and ultramafic rocks derived from layered intrusions. These layers result from fractional crystallization in magma chambers and may be preserved after metamorphism. 3. Deformation-related primary structures. Tectonic forces acting on a rock before or during metamorphism may influence its structure. A. Folds and faults. Pre-existing folds in sedimentary or igneous rocks may be enhanced or modified during metamorphism. Older faults and fractures may be reactivated and filled with new mineral growth. B. Shear zones. Pre-existing fault zones may develop into mylonites during intense metamorphism. These zones record ductile deformation and indicate past tectonic movements. C. Unconformities. Some metamorphic terrains preserve evidence of unconformities from their original depositional environment. These indicate breaks in the geological record before metamorphism occurred. Conclusion. Primary structures in metamorphic rocks are vital clues to understanding their geological history. Even after metamorphism, remnants of sedimentary, igneous, and tectonic features can provide insights into the original rock type, the environment of deposition, and past geological processes. Recognizing these primary structures helps geologists reconstruct the sequence of events that led to the formation of metamorphic rocks and provides valuable information about Earth's crustal evolution.